Hello everyone, welcome back. Today's topic is about belief representation, which fundamentally deals with the position of the robot on a map. That means you are representing the position of the robot on a map using a few typical techniques, physical appearance, and then the belief representation has some fundamental issues that differentiate between map-based localization systems. That two different concepts that would include the representation of the position of the robot itself on a map with a unique possible solution. That's the primary concept, and the second concept would be how to represent this position in a typical model map. That means in a map how you are representing the model. So these two fundamental issues that always exist in case of a belief representation. So belief representation in case of mobile robots is very much important because the belief representation will tell you how the robot's positional variance or how the robot movement that exists in a typical map that you have planned to implement in a typical machine like a Mars machine or something. So belief representation plays a very huge role in case of identifying the motion. So let us go deeper into the aspects of belief representation. So belief representation is classified into two different types. The primary one is single hypothesis, and the second one is multiple hypothesis. The word hypothesis states that there is a probability that the robot is present at that particular position. So it exists in two ways. One is a single hypothesis that will give you a pinpointed way of representing a robot. Let us go deeper into the single hypothesis belief, followed by multiple hypothesis belief. So in case of a single hypothesis belief, we have the belief representation is always expressed as a single unique point solution. That means you have a unique solution for your robot's position on the map. It has some potential advantages and disadvantages. So it got a unique belief that there is when you're dealing with a single belief, that means you don't have any positional ambiguity. And the second would be it facilitates your controller to take the decision at the cognitive level, which is the primary level. So that gives a quicker output, and then it facilitates the quicker update on the map. So you will get a quicker update. So since it is a single hypothesis belief, you need not to compare with any typical other hypothesis that is existing in the system. So you have a single solution. Single solutions are always pinpointed, so it gets easier and quicker update on the map. And the private there are two disadvantages as far as few authors mentioned in a lot of textbooks. So the possible thing is all the sensor noise that exists in this typical representation will be added, and your single point solution sometimes or most of the times they may go wrong, and it has some uncertainties to your end effector. For example, in case of mobile robot, you have a rotary motor in most of the cases. So this rotary motor will give some end effector noise in terms of its the rotation or there's jerky motion, something like that, when the terrain is uneven. The best example for this is a Mars terrain. So you don't know what is the terrain there. So it is always some sort of error that exists in case of your end effector. So that's the primary drawback in case of a single hypothesis belief representation. So let us check some examples of this single belief representation. So if you just check the single hypothesis belief, you have the highest probability of a particular position x at only one point. So you have the maximum value, which is considered as a maximum probability of the position, as shown in the graph. So the graphical representation clearly states that you have a primary single hypothesis belief, which is only a single point solution. So you can discard the lot of changes that occur in the position, and you will get the maximum or the highest probable position to be the maximum point in this peak, as shown. And if you just check the single hypothesis belief in case of this example, you have a robot's position that is represented as a dot. So this dot will change its position based on the robot's moment, which will be given by your IMU sensors, which will give in terms of like 3 degree or 4 degree of output. That would include your x, y, and then your z. Generally in indoor robots you have a flat surfaces, so z will not play a major role, so in that case we'll go with a theta. So theta could be in terms of x and y orientation, or maybe a simple theta in terms of its axial thing. So in case of this example, it is very much clear that in single hypothesis belief you believe in a dot, just like your Google Map blue dot. So the map is represented with a realistic object. So you have some doors here, and you have some corridor here, you have some windows, you have some partition sections. So all these things are converged onto a single line. So wall exists in terms of, let us say, centimeters to meters in certain cases. So all these things will converge, or it will just decompose into a simple line. So you represent this particular thing in a map which is given, which is shown here. So in case of single hypothesis belief, in certain maps you represent your doors, windows, and all the realistic objects that are present. So let us move on to the second example. So in this case of single hypothesis belief, you have a line-based approach, which will not give you the exact shape, size, or what kind of object it is, but it will tell you like what is the entrance and what is the exit. So this is pretty easy. So in this case, in the example, it is very much vivid that you have x, y, and theta, which are the variables pertaining to this dot. That means the robot. So as the robot commences towards different positions, so there will be a highlightation in the lines which has the probability of obstruction. So this is a kind of representation which is typically a line-based approach. So line-based approaches are very simple, and you need not to work on a lot of math. So these typical single hypothesis belief has a very good refresh rate that will give you a very quick, very advanced update on the map about the position of the robot. So these are certain advantages of a line-based map approach. So let us move on to the next example, that is occupancy-based grid. So in this case of occupancy-based grid, all the entire map area is converted into individual zones or individual blocks. So each block represents a significant position of the robot. So for example, you just check the robot's position is exactly located at a particular box region which covers 2 to 3 boxes. So the biggest advantage of the occupancy grid based approach is your decomposition strategy, or the strategy of decomposition of your map will be very nominal. So in case of a line, you have to understand like which area it is located in with, but in this case you find out which box it is located with, and then it is pretty easy to approach. So this typical approach, you can see in a lot of old age movies that approaching of a ship to the ship then in which a typical person is traveling, or all the radar based systems used this typical single hypothesis belief approach, which is typically a grid based approach on the screens. Most of the screens are dot matrix those days, so you have a very quick update on each dot matrix that is present. So this typical approach does not require much computation, unlike your the previous two approaches, which will give the line based approach as well as your realistic map approach. In both the cases you require a good computation, but the computation power in this case which is required is typically very less. So generally when you want a quicker update on the map, we can actually look or a plan for using such type of displays fundamentally, or a map displays that will look something like this. And you have a nodal approach. Nodal approach requires a lot of computation. That means each and every node represent the position of the robot. For example, in this case you can just check node I would represent the current position of the robot. So the all possible nodes will tell how the robot can travel through this typical approach. So this is a topological approach where the commencement of robot you can clearly visualize on the screen using this, but it requires a lot of computation power. So let us move on to the next part, that is multiple hypothesis belief. So multiple hypothesis belief is always expressed as multiple possible positions on the map. That means there is a highest probability rate has to be considered, or it gives you a lot of solutions, which makes the system very complex. So you have more number of positional updates, which requires a good computation. Robot can explicitly maintain uncertainty regarding its own position. So this is one more problem that exists in case of multiple hypothesis belief. It has some potential advantages and disadvantages. So it gives you more accurate position on the map. Just like in case of your Google Maps, you require 3 satellites in order to tell you like what is your GPS location, but it requires a lot of computation. So your system has to be really good enough with the computation. So you have more number of possible states. That gives you again it's an advantage as well as disadvantage in most of the cases. If your computation power of your controller or your processor is good, so more number of possibilities are there, so you will get the best solution out of it. So you'll get the best output of representing the position of the robot on the map. And it has two disadvantages. It has a very expensive decision making, as you can see, and the computation time equally is more. In case of single hypothesis belief, you have a single point, that's it, you compute that, you will consider that to be the most possible solution, that's it. So in case of multiple hypothesis, you will get different solutions, so different solutions, you have to find the best solution out of it. So that's the problem here. This if you could just check here, there are multiple possibilities or multiple probabilities of the position x. Which one is the maximum probability would be considered as the best solution in this example? It's fundamentally a Gaussian distribution of your position x. Let us move on to the next part. So in case of a continuous map, we have seen a continuous map. We will find out like what is a continuous map in the later part of this subject. But in this case of continuous map, we have the position probability of x, which will vary in this typical pattern. So this is one example like how we are multiple hypotheses. So the best possible solution in this given example would be this or this, depending upon the position. So position also varies with respect to time. So if you consider time, so time and probability, you have to derive some function out of it. So the position x varies with respect to time in this case. The later part would be like how to track this multiple hypothesis belief. So you just check, you have in the very first figure, you have a typical inlet for the robot. So the possible inlets in this case would be this one. If you could just identify, this one is one possible solution to get out of this particular map, or this one, or this one, or this, or this, but not these two, because there is dead ends there, so you cannot make your robot to move in that particular area. So in this case, if you can just check the second figure, you can just check your belief representation color has been changed to the highest possible in this region, but not in this region. It is very much vivid in this case. So later, as the robot passes to the next position, so it can enter in one possible inlets or the positions. So the distribution would have been considerably become less because it has chosen one particular path. In the later case, you can just check in the third figure, you can just visualize. So there is a density of highest density of position here, and later it passes to this one and it exists. So the darker color represents the highest probability in this case, where the lighter color represents the lower probability. So say, multiple hypothesis tracking, it happens in a step-by-step fashion, but the biggest problem is the computation. This example has been taken from W. Bogard, who is a very good author. So you can just refer that author for your for further study on the multiple hypothesis tracking. And after the belief representation, like how you represent your map, once the belief representation is done, you have to go with a map representation. So let us go deeper into it. So this map representation always have three fundamental relationships that everybody has to understood while choosing a particular map. So the primary one is the precision of the map, like how you choose your map, how you appropriately choose your map, and how much precision you require so that the robot achieves the goal. But if you are choosing, for example, in the previous case, if you are choosing a map which has more changes or more areas, so you have to choose a highest precision in order to point out the robot's position or your belief representation. The second would be like how your features are represented. For example, if you want to represent X, like which sensor you have to use, like which typical sensor you have to use, or which feature on the map we have to use. So how this sensory data interprets or gets fit into the map. So that's the second fundamental relationship everybody has to understand. The third one is the complexity of map representation. It has a very direct impact on the computational complexity about like localization and navigation. So every frame or every refresh point will tell you the update on the map. So if your map is huge, the refresh time would take a larger thing. So these three are the fundamental relationship which we have to understand before choosing a typical map for your belief representation or for your robotic application. So let us go deeper into it. If you could just check, the biggest challenge is unknown area. So in case of a Mars rover, we have to select a particular region in order to explore. So that becomes a local map. This is like overall map. This map is represented in terms of like a different terrain. So terrain is the scope. So you have to just look into the different terrains. You can just check some hilly terrains here, some 3 hilly terrains and 1 large hilly terrain, and some craters here, some unknown regions here which are not uniform. So when you want to implement in one particular area, first we have to understand like what is the map of that area, what is the altitude of the area, how much unevenness we have to understand. For example, these are certain considerations, or what kind of sensors I have to use in order to make the map update very quicker. So complex map like this will require huge data and huge computation power with the processor or whatever controller you are planning to use. So we have one typical method, which is a continuous map representation method. So in continuous map representation or continuous value map representation method is like it will decompose the environment into any typical continuous space into a line. So that means your robot will move only in a 2D representation. So it will allow the map in only like a 2D representation. So continuous map representation is always preferred because you need not to worry about the third dimension, which is your altitude. So mostly it is preferred by most of the mobile robot makers. So this is very simple and easy approach. Let us go deeper into it. So if you could just check the typical continuous map representation here. So the cumulative map will look more or less like multiple polygons that are arranged in an order. You have some desks, you have some sofas, you have some stairs here, you have some corridors or pathways, we have some work tables, and then all the things are continuously attached with each other. So that, and hence the name, the continuous map. So a continuous map will give you a full picture of the space which you are planning to implement your robot's movement. So that's all for the day. Thank you. Thanks for watching the video.